Hi everyone, welcome to our next video. We're going to be working in this unit on applications of derivatives, and the first thing we want to talk about is optimization. We're going to do an overview and a process on some of these, but basically optimization is just dealing with extrema, maxes and mins, whether relative or absolute. So let's get started. Optimization is one of the earliest applications of calculus. Because it deals with extrema, maxes and mins, it's used in business, marketing, economics, to find things like greatest profit, least cost, the least amount of time, the most materials, maximizing the volume or the area, finding the greatest value or the least value, which makes sense. All those words have to do with a max or a min. It evolved out of curve sketching, of course, because you're dealing with maximum points and minimum points. And we're going to talk about volume and area, cost, revenue, profit. You can see here inventory, distance, time, anything that requires us to optimize something, a material or a value. So here's a traditional optimization problem, the box problem. Most of you have at least seen this problem before, but if you haven't, we're going to go over it here. This is where you are given a rectangular piece of cardstock, and it's got some dimensions. This one is 17 by 11. And then what the problem is that you're going to cut squares out of the corners of the box. See the picture? Cut the same size squares out of the corners, so that when you fold up this tan part, you fold up these edges, then it makes a box without a lid. And so what you want to do is what size, you're trying to find the size of the squares so that the volume of the box is a maximum. Okay, so a traditional algebraic response is to set up the dimensions of the box, what the box would be. So you would look at this would be the length of the box, right? And that would be 17 minus 2x. And then the width of the box would be this size, and so you would say that that was 11 minus 2x. And then if you fold up the edges, that would be the height of the box, and that would just be x. So an algebraic solution would be to set up the volume is going to be length times width times height. We don't care that it doesn't have a lid. We're not dealing with surface area. So the volume would be something like this. Okay, and then what we did in an algebraic is we used our calculator, and some of the optimization problems don't require a lot of calculus to do because we have calculators that we can put them in and we can look for the maximum point. And so when we do that, then we would, I would just put this in my calculator, and then I would solve it to find the greatest point on the graph. So when I put this in my calculator, I reset the window, so I went from 0 to 10 on my calculator. And then I went from 0 to about 200 here, and then down here I went to about negative 150. And I got something that looked sort of like this. Okay, something like that. So you can see very clearly that we have a max and a min. And when I used my calculator to find the max, it gave me this point was 2.1778. 182 point something, 182.97, okay? And so since I can clearly see on my calculator that that's a maximum, this is my x value, this is my y value. So what I'm finding is this is the volume, and then the x value is the size of the squares. So this is a traditional way then to do this type of problem, is finding the max or the min of a function. We can also use calculus to find these problems. And so that's what we're going to do on the next page. Okay, so here's the same box problem from a calculus point of view. So we know that we can find the max or min using either the first and or the second derivative test. So we're going to start with the same function. And this is, of course, what it looked like. 17 minus 2x, whoops, sorry, and 11 minus 2x. And so what we want to do is we do want to take the derivative of this. And it's most likely, it's going to be easier, believe it or not, to multiply it out before we take the derivative. So hold on just a second. Okay, so I took a second and went ahead and multiplied some of this out. I needed a calculator. And you know me, if I went to get a calculator, it's serious. So I end up with this, and so your volume function will be 187x minus 56x squared plus 4x to the third. So when we take the derivative of that, let me move that up just a little bit. We take the derivative of this, we're going to get 187 minus 112x plus 12x squared, which is quadratic, and we know from the previous screen is not going to factor. So if we use the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. And I have a little program on my calculator, so when I did that, I got two answers. And one of my answers is 2.1778, and the other is 7.155. Both of them are positive, so we can't eliminate any answers based on one's negative, one's positive. But if we go back to our original problem, if x is 7, then it won't fit width-wise, right? It'll be 7 plus 7 is 14, which is wider than the width. So we reject the 7.1, and we know that the corners need to be 2.1778. We can verify that this is a maximum value if we take the second derivative, right? And the second derivative would be negative 112 plus 24x. And if I put the value in there, the value is negative, right? So that would mean that the second derivative is negative and concave down. And if it is concave down in that interval, that would indeed be a max. So that would be our solution. So on this screen, there are some steps here. The first thing we want to do when we're doing optimization problems is to label and draw a picture. Write formulas based on whether we're doing area, volume, of the quantity that we want to max or minimize. Use it to simplify, take the derivative and find critical numbers. Step 5 is verify with critical numbers. It's not enough just to find the critical numbers. You've got to figure out which is a max, which is a min. And then use either the first or the second derivative test, and then make sure that you're finding what the question actually asked for. Okay? Okay, so here's a different example. We want to enclose a field with a fence. We're going to assume it's a rectangular field. We have 500 feet of fencing and a building on one side of the field. So the first thing we need to do is draw a picture, right? Here's the building. This is the building. And then I have a rectangular pen, right? And so the fencing will need to be on this red part right here. This is my fencing. These will be the same length, and this will be the same length as the side along the building, but I don't need fence along the building. So the perimeter of my field is going to be 2x plus y, and the amount of fencing that I have is 500 feet. So I can set up that constraint. It says determine the dimensions of the field that will include the largest area. All right, so I've already submitted the variables to my picture. And so I want to find the area. The area of this is going to be x times y. Too many variables, so I'm going to do substitution. I'm going to solve this 2x plus y for y. Okay, and that gives me 500 minus 2x. And then I'm going to substitute that into my area formula so that I have one variable. I have one expression in one variable. So I have 500 minus 2x. So the area is going to be x 500, 500x. That's funny. Okay. 500x minus 2x squared. All right, now I need to take the derivative. Don't forget to take the derivative. okay, and set it equal to 0. So negative 4x equals negative 500, and so x is going to be 125. Yes. Okay, so 125. So that seems like that could actually work, but let's take the second derivative of the area, which is just going to be negative 4. So since it's negative everywhere, that's going to be concave down, right, like that. So that indeed shows, since that's going to be less than 0, it shows that 125 is a maximum. So then in order to figure out what y is going to be, I would plug this 125 back into my original formula, and so that would be 125 plus y is 500. So if this is 250, that means y needs to be 250. And so I have, and this is in feet. So these are my dimensions right there. Okay, let's do one more example. This is find two positive numbers whose sum is 20 and whose product is as large as possible. All right, so two positive numbers. I have one positive number would be x, the other positive number would be y, and it says that their sum is 20, and then I want to maximize their product. So once again, I don't really need a picture. I have two variables. I set up the constraint, and then I set up the function that I want to maximize, because it says large as possible, so I want to maximize it. I'm going to solve for y, put it back into my problem, and simplify just a wee bit before I take the derivative. Don't forget to take the derivative. I did it again, x times 20, I don't know what's up with that. All right, so take the derivative, and I get 20 minus 2x, set the derivative equal to 0, and solve. X is 10. Okay, so that's a positive number. If I take the second derivative would be negative. So this is concave down, because it's less than 0. So that would indeed be a maximum. So if x is 10, then y would be 10. And those are the two positive numbers. So we're going to do a lot of these in class, different things from economics and profit sharing and things like that. So anyway, I hope you took good notes, and I will see you in class.